Good morning, professors. I am Ashish Rekhani, and me, along with my friends Anushka Srivastav, Vibhu, and Deepiha, will be presenting on the use of AI and deep learning to solve the traveling salesman problem. In this presentation, we will be covering the use of the transformer network to solve this particular problem. This presentation is inspired and based on the research paper titled The Transformer Network for the Traveling Salesman Problem by Professors Xavier Bresson and Thomas Laurent. Let's begin. First of all, let's understand what the traveling salesman problem is. Given a list of cities and the distance between every pair of cities, the problem is to find the shortest possible route that visits every city exactly once and returns to the starting point. This problem was first formulated by William Hamilton, and it's a very famous NP-hard problem, meaning there is no polynomial time known solution for this problem. But why is this problem so important? The traveling salesman problem, or TSP, actually belongs to the larger class of routing problems which are used every day in industries like warehouse management, transportation, supply chain hardware design, manufacturing, and so on. Slightly modified, it appears as a subproblem in many areas such as DNA sequencing. It also appears in astronomy, as astronomers observing many sources will want to minimize the time spent moving the telescope between the sources. In such problems, the TSP can be embedded inside an optimal control problem. Let's consider the example shown on the slide. Given this particular graph, the shortest possible Hamiltonian cycle, which is a cycle which visits the start node and visits every other node exactly once. So in this given graph, the shortest route is visiting starting from the node A, we move on to node B, followed by nodes C, D, E, and back to A. The cost in this travel is basically 12 plus 3 plus 2, that's 17 plus 4, 21, and plus 8, 29, which is the minimal cost. Now, considering the importance of this problem, and since exhaustive search of all the possible paths has a complexity of n factorial, this makes it extremely difficult and also the reason for its extensively studies in optimization. This problem is used as a benchmark in optimization problems. It has led to many important discoveries and optimization techniques like cutting planes, branch and bound, local search, as well as simulated annealing. Traditionally, traditionally the combinatorial TSP belongs to a class of combinatorial problems. Combinatorial problems are the problems consist of finding an object from a finite collection that satisfies all constraints. Traditional approaches include exact algorithms and approximate or heuristic algorithms. Exact algorithms, as the name suggests, give the optimal answer and include various known algorithms and techniques like exhaustive search, dynamic programming. These algorithms, although guaranteed to find the exact solution, will become quickly intractable as the value of n increases. That is, as the number of cities increases. Second class of problems is the approximate or the heuristic algorithms. Here we trade optimality for computational efficiency or time complexity. A heuristic, that is a simple rule or an estimated guess, is designed and applied iteratively to get the solution. The complexity of such problems is polynomial, and the quality choice is dependent on the approximate ratio that characterizes the error. Now let's study about some exact algorithms for this particular problem. First of all, we have the dynamic programming approach. Secondly, we have the Gurobi, which is the general purpose integer programming solver, which also employs cutting planes and branch and bound techniques. Thirdly, we have the Concord. Concord is a highly specialized linear integer programming. Along with it is embedded cutting planes and branch and bound techniques specially designed for the traveling salesman problem. And lastly, the traveling salesman problem can also be modified or formulated as an integer linearing problem and solved therefore. Let's understand more about Concord. Concord is a problem for solving the travel salesman problem. It was first written by David Applegate, Robert Bixby, and William J. Cook in ANSYS C. It's a highly specialized version of linear integer programming using cutting planes and branch and bound techniques. Concord is widely regarded as the fastest exact TSP solver for large instances to currently exist. Overall complexity for Concord is big O of n to the power 2.5 multiplied by B of n. O of n to the power 2.5 is for the linear programming and multiplied by O of B of n for the number of branches to be explored. Concord's TSP solver has been used to obtain the optimal solutions to the full set of 110 TSP library instances, with the largest having as many cities as 86,000. Next, we'll be studying about approximate algorithms, and Deepiha will be explaining the same.